Hello, in this video we're going to talk about pointwise and uniform convergence of functions. So let D be a subset of R and Fn from D to R be a sequence of functions. We define the pointwise limit of these functions as just like the normal taking the limit of each of these sequences. So for every x, you take the limit of Fn of x as n approaches infinity. If that limit exists, then we say f of x is equal to that number. So E is the set of all the points in D such that Fn of x converges. Then f of x is defined as the limit of Fn of x. So this is called the pointwise limit. So Fn converges pointwise, and the notation is that to f on the set E. So let us do a few examples on that. Okay, so the first example is a sequence of functions fn from 0, 1 to r given by fn of x equals x to the power of n. So if you look at f of x, that would be the limit fn of x as n approaches infinity, which is the limit of x to the power of n as n approaches infinity. So we know what that is. If absolute value of x is less than 1, then this would be 0. So this would be 0 if x is anywhere from 0 to 1 but excluding 1. And it would be 1 if x is 1. Because if x is 1, then every term of the sequence would be 1. So this would be the limit of this sequence. Part B is asking us to find the limit of a different sequence. So this one is the limit of the sequence e to the power of negative nx squared as n approaches infinity. Okay, so as n approaches infinity, e to the power of nx squared, the exponent approaches nx squared approaches infinity. Negative of that approaches negative infinity. So e to the power of negative nx squared is 1 over e to the nx squared. And nx squared approaches infinity, and e to the infinity would be infinity, so this would approach 0. However, there's one issue with the argument that I just made, and the issue is when x is 0. Because if x is 0, then nx squared does not approach infinity. So that would be problematic. So we have to take two cases. If x is 0, then g of 0 becomes the limit of all of the terms are just 1, which is 1. So now assume x isn't 0. So assume x is not 0. What I need to do is to show that e to the power of nx squared approaches infinity. So how do we do that? We have done this one before when we were doing that example of a function that is not analytic but it is infinitely differentiable. So that's the idea. E to the power of nx squared is equal to the sum nx squared to the power of k over k factorial, k equals 0 to infinity. Since all of the terms nx squared to the power of k over k factorial are non-negative, or in fact they are positive, this is at least, I'm going to take one of the terms that has n in there. So this is at least nx squared over 1 factorial. So this means if I look at e to the power of negative nx squared, first of all, this is positive, and second, this is less than or equal to 1 over nx squared. Limit of 1 over nx squared is equal to 1 over x squared times limit of 1 over n as n approaches infinity. But as n approaches infinity, 1 over n approaches 0. So this becomes 0. So then, by the comparison lemma, limit of e to the negative nx squared is 0 when n approaches infinity. So to summarize, g of x is going to be 0 if x is not 0, 1 if x is 0. Okay. Let's look at the last example. The last example is a function that is a little bit weird. It's not really a continuous function. So your function is 0 when x is m over 2 to the n for some integer m. And if you recall, m over 2 to the n was called a dyadic number, a dyadic rational. And it is 1 when x is not in that form. So let me look at some examples of this h. So h1. So let's look at h1. If you look at h1, so this is y equals h1 of x. If you look at that, we have for every x that is of the form m over, if n is 1, it would be, x would be m over 2. So the denominator would have to be 2. So 0 is one of them. So at 0 you have 0. So at those points you get 0. At 1 over 2, 0 over 2, 1 over 2, and 2 over 2. So let me put that a little bit further. So 1 over 2 and 1 and 0. At these 3 points you have 0. At every other point you're going to have 1. So this is the graph of the function. Now, if you look at h2, let me draw h2 in the same graph with a different color. So perhaps I'm going to change the color here to green, and I'm going to use a third color for h2. h2 would be anything that is of the form m over 4. So it would be 1/4, 0/4, 1/4, 2/4, 3/4, and 4/4. At those points you get 0, and you're gonna have holes here, so it would be similar to the previous one except for a couple holes, extra holes. So this would be y equals h2 of x. It's almost the same thing as the previous one except for that point, for those points. h3 you would add some more points. So here, maybe I'll use a different color. You add some more points. So here, and then the original points are still going to be there. So this is supposed to be on the x-axis. And then we're going to have a bunch of holes here. So it's pretty much the same thing except that you're adding more points. So if your number x is not of the form integer over a power of 2, then every hn would be just 1. So h of x is the limit as n approaches infinity of hn of x. So let's see what happens. If x between 0 and 1 is not a dyadic number, then hn of x would be always 1 for all n. And that means h of x would be just 1 because it's just a limit of 1. If x between 0 and 1 is dyadic and x is m over 2 to the power of n for some integer integers m and n, with n being positive, hn of x, hn plus 1 of x, all of these are 0, because if you can write down x as m over 2 to the n, you can also write it down as 2m over 2 to the n plus 1, 4m over 2 to the n plus 2, etc. So everything after hn would be 0. And therefore, if you take the limit of that, it would be 0. Limit of the hn of x. So this brings us to the final answer. To summarize, h of x, which is the limit, the pointwise limit of that sequence of functions, is 1 if x is dyadic rational. Yeah, so dyadic rational. It would be 1 otherwise. So if it's a dyadic rational number, it would be 0, because at some point all of the terms of the sequence are 0. And if it is not, meaning that either the number is x is irrational, or it is irrational, but in the denominator it's not a power of 2. So it is something like 3/10. There is a 5 at the bottom, or 17 over 18, something like that. So for those, the limit would be 1. For everything that is dyadic, the limit is 0. Okay, so these 3 examples are in fact interesting examples. I will make a point about these examples. Let's look at the examples that we did in this these 3 examples. If you look at the first one, x to the power of n, every single one of these functions is a continuous function. X to the power of n is continuous. However, the limit is a piecewise defined function and is not continuous. If you look at the second one, not only all of these functions are continuous, but they are also differentiable. E to the power of negative nx squared is a differentiable function. But if you look at the limit is not only not differentiable, but it's even not continuous. So the sequence of functions are all continuous and differentiable, but the limit is not even continuous. And if you look at the third example, so if you look at this example, every single one of these functions, hn of x, is integrable because it is continuous over the entire interval from 0 to 1, except for a few points. h1 has 3 points of discontinuity. h2 has 9 points of discontinuity. 5 points of discontinuity. 0, 1/4, 1/2, 3/4, and 1. These 5 points. h3 of x would have 9 points of discontinuity. m over 8 when m goes from 0 to 8. And so on. So each one of these hns are integrable. However, when you look at the pointwise limit, you get 0 when x is a dyadic rational, 1 when you get something that is not dyadic rational. Since dyadic rationals are dense and irrationals are also dense, this function would not be integrable. So all of the lower sums would be 0, all of the upper sums would be 1. Not very difficult to see. So bottom line is, we have sequences of continuous functions that the limit is not continuous. We have sequences of differentiable functions that the limit is not differentiable. And we have sequences of integrable functions that the limit is not integrable. So in other words, this pointwise limit that we talked about is not a very good definition. It's not very useful. It doesn't translate the properties of the sequence to the limit. So the question is now, is there a way to define this limit in a better way that gives us a better conclusions? Is there a way we can define convergence that translates these properties? And the answer is in the next definition. Okay, so we say a sequence of functions fn converges uniformly to a function f if the following holds. For every epsilon positive, there is an n that for every n greater than or equal to n, and for every x in D, this is what makes it uniform. The difference between fn of x and f of x is less than epsilon. So, not only the difference between fn of x and f of x is less than epsilon, but this works for every single x. Not only fn converges to f, but it converges uniformly. So what does that mean? Let's look at the examples that we had up there. Let's look at the very first example. So the very first example was the x to the power of n. So the first one was x. The second one is x squared. The third one is x cubed, and so on. So of course these approach the limit that at 1 it's 1 and everywhere else is 0. So this is the limit. However, what happens is they don't approach at all points in the same rate, If you look at points that are here, they approach to these much slower than points that are close to 0. They approach to 0 much faster. So because this rate is not the same everywhere, we cannot find one epsilon, we cannot find one capital N that works for all x. And this is something I will discuss in the next example. One thing that is fairly clear is that if the convergence is uniform, then it would also be pointwise. So if fn converges to f uniformly, then fn would converge to f pointwise as well, but not the converse. Okay, so let's look at that example. Check if each of the convergences in example 9.20 is uniform. So as we discussed, this doesn't seem like it's uniform. So the first one is the convergence is not uniform. Okay. So since we are trying to prove negation, we're going to assume that it is uniform. Now, what we want to do is we want to choose some epsilon in this definition and get a contradiction. So how can we do that? We could take an epsilon that if we have to take our function and thicken that and also thicken it here, but we want to get a contradiction. So we're going to take epsilon. This is the difference, the distance between the top and bottom. We're going to take our epsilon in a way that 2 epsilon is going to be less than this whole distance, or even equal would be fine. So let epsilon be 1/2 in the definition of uniform convergence. Okay, so I'm using proof by contradiction. So on the contrary, assume fn converges to f uniformly on the whole interval 0 to 1. So this means for every x inside 0, 1, well, there is some capital N. There is some capital N in N such that for every n greater than or equal to n, and for every x in there, the distance between fn of x and f of x is less than 1/2. Okay, so we know that. Now what I'm going to do, I'm going to just basically substitute fn of x and f of x by the values. So this means if I substitute here, I get x to the power of n minus. So if I substitute that by for all x between 0 and 1, because between 0 and 1 that would be f of x would be 0. Now I can allow x to approach 1. So let x approach 1. So take a sequence that approaches 1. This shows that 1 minus 0 must be less than 1, which is a contradiction. So therefore the convergence cannot be uniform. So if this approaches 1, and I can choose that, for example, choose xn equals 1 minus 1 over n. This approaches 1, therefore the 1 minus, I guess, xm, because I don't want to mix the n and m up. So choose that, and this approaches 1, therefore x to the power of n approaches 1, so 1 should be less than or equal to, because you're taking the limit, so it would be less than or equal to. Okay, so that's a contradiction. Okay, so now we're going to do the same thing for the next one. If you look at the next one, let's first get an intuition on whether these convergences are uniform or not. The functions were e to the power of negative nx squared. So the first one is e to the power of negative x squared. So at x equals 0, it is 1. In fact, all of them at x equals 0 are 1. And when x goes to infinity, they approach 0. So something like that. And when x goes to negative infinity, they also approach 0 because you have x squared, which is positive. And the next one would be the same shape, basically, just goes to 0 faster. And so on. As you see here, the rate of approaching to the limit, which would be this function, is slower than the rate up there, the rate at this site when you approach infinity, which means it would not be uniformly, it doesn't converge uniformly. So we claim Gn does not converge to G uniformly. We're going to do the same thing. So on the contrary, assume Gn does converge to G uniformly on the entire real line. So we're going to do something similar. Let epsilon be, we're going to avoid the top. So let epsilon be 1/2 in the definition of uniform convergence. So what we get is this. There is some capital N in N such that for every n greater than or equal to n, and for every x in R, the distance between Gn of x and g of x is less than 1/2. Okay, so let's now substitute this by some x that is non-zero. That gives us Gn of x is e to the power of negative nx squared minus 0, because we know g of x is 0 when x is not 0. So that's less than 1/2. Now take a sequence, let x equals 1, maybe something that approaches 0. So let's say 1 over m. So this gives us e to the power of negative n over m squared is less than 1/2. Now allow m to approach infinity. We obtain e to the power of n is a fixed number over m squared. N over m squared approaches 0, so that would be e to the 0. So that becomes less than or equal to 1/2, which is a contradiction. Okay, so this convergence is also not uniform. Finally, we will look at the last one. So similar to the previous one. Similar to above, we will show the convergence is not uniform. Well, it would be quite similar. On the contrary, assume Hn converges to H and let epsilon be 1/2. So that means there is some integer n, positive integer n, such that for every n greater than or equal to n, and for every x inside 0, 1, the distance between Hn of x and h of x is less than 1/2. Let x be 1 over 2 to the power of n plus 1. Now, we know that x is dyadic. So since x is dyadic, we obtain h of x is, I believe it was 1. But since x is not of the form m over 2 to the n, we have Hn of x is still going to be 0. So that means Hn of x is 0, h of x is 1. So that's less than 1/2, which is a contradiction again. So this sequence is also not going to converge uniformly. There is a convergence, but it's not uniform. Okay, so this is these are 3 very important and interesting examples. So last thing we're going to do is we're going to look at the one example similar to what we did before, but this time the convergence is in fact uniform. So find the pointwise limit of that. So if you look at f of x, which is the limit as n approaches infinity of x to the power of n, this is going to be 0 for all x between -1/2 to 1/2. And this is because of an example we have done before. So now we're going to have to show that the convergence is uniform. So let epsilon be positive. We will have to find some capital N that the difference between xn and 0 is less than epsilon for all x inside the interval. So this is what we need to do. If you look at absolute value of x to the power of n, that's less than or equal to 1/2 to the power of n. And we can make this one less than epsilon. How? We know 1/2 to the power of n approaches 0. So we're going to use that. Since 1/2 to the power of n approaches 0, there is some positive integer n such that for every n greater than or equal to n, 1/2 to the power of n is less than epsilon. Now, if n is greater than or equal to n and x is in the interval -1/2 to 1/2, then the distance between x to the n and 0 is going to be less than or equal to 1/2 to the power of n, which is which is less than epsilon by assumption, by what we found here. So we know there is an n that after that point 1/2 to the power of n is less than epsilon, and that's exactly the n that I chose. and this means xn approaches 0 uniformly on the interval -1/2 to 1/2. So I'm making a point by this example. If you look at the example that we did earlier, it was the same sequence of functions, the very first example. It was x to the power of n. The difference though was the domain. So if you take the sequence of functions x to the power of n over the domain 0 to 1, that is not going to converge uniformly. But if you look at the exact same sequence of functions over the interval from -1/2 to 1/2, that would be convergent uniformly. So it depends on your domain. It is very important to note that. Okay, so this brings me to the end of this video. So next time we'll continue with the discussion on uniform convergence. Right, so it brings me to the end of this video. I will see you in the next video.